This is the second and last lecture of Chapter 11, Oxidation Reactions in Organic Chemistry. As a review, last lecture we covered the following. We defined oxidation. We determined how to calculate oxidation states of carbon atoms. We looked at various oxidizing agents, including potassium permanganate, the Swern oxidation, the Des-Martin oxidation, and PCC, for example. We also looked at the oxidation of alcohols and aldehydes. Next, we looked at the oxidation of diols using periodic acid, and we looked at the applications of oxidation reactions. In today's lecture, what we look at here is the oxidation of a different functional group, alkenes. You will discover that you can carry out the oxidation without the cleavage of the carbon-carbon double bond, or we can carry out the oxidation of alkenes with the cleavage of a carbon-carbon double bond. Of course, as you can imagine, the reagents for these two reactions are different. And then we look at the oxidation of alkynes, and we'll look lastly at the oxidation of substituted benzenes. Okay, so let us start our lecture here. With the appropriate oxidizing agent, we can take a double bond, an alkene, and we can oxidize it to an epoxide. Another name for the epoxide is an oxirane. This oxidizing agent here is a particular one or particular ones, and we'll discuss that. Or we can take an alkene and we can oxidize it to get a 1,2-diol. Here's the 1,2-diol, 1 and 2 diols, without again breakage of the bond. So let us look at these reactions. First reaction here is taking the alkene and converting it into an oxirane or an epoxide. The reagent that's used is a peroxy acid. Here is a specific one that's commonly used in organic chemistry. It's called metachloroperoxybenzoic acid. It's really benzoic acid with an additional oxygen. And it's called MCPBA. So you will see this written as MCPBA. As chemists, we understand it means metachloroperoxybenzoic acid. It's an oxidizing agent that will convert an alkene into an epoxide or an oxirane. As you know, I could not leave this without explaining how it works. So here's how it works. Here's your peroxy acid. We just use R here to indicate a different group bonded to the peroxy acid functionality. So here's your extra oxygen. And as you can see with these electron movement here, this oxygen is now incorporated into the carbon-carbon double bond. The other product, as you can imagine, is your carboxylic acid. So this is essentially the mechanism, a one-step mechanism. We call it a concerted mechanism because it occurs in one step. All the electrons move as in one step. Here's an example. So you have your alkene functionality here. Just put MCPBA. We as chemists, we understand what MCPBA means. It means metachloroperoxybenzoic acid, and we get your oxirane or your epoxide. Epoxides are very important molecules in, or functional groups in, organic chemistry. They are very reactive. As you can see here, it's a carbon and a carbon that's bonded to a very electronegative oxygen, which means that these carbons here are electrophilic or partially positive. In an acidic medium, H+, as you can imagine, the H will be protonated, and if the solvent is water, it can attack to get here this intermediate, and the final product is a 1,2-diol. In this case, it's a transdiol. Keyword, you'll see why I am emphasizing trans in a second. So this gives a transdiol. In the presence of water, if it were a basic medium, as you can imagine, the OH can attack this carbon, which is partially positive, electrophilic, and here we can form the same trans 1,2-diol, same product, but under different reaction conditions, specifically acidic reaction conditions and basic reaction conditions in the presence of water, to give the trans 1,2-diol. So here's an application of this reaction. So if you had your alkene right here, and the first reaction is MCPBA, you get your epoxide. A second reaction is the hydrolysis of the epoxide. Under acidic conditions, what you have here is your trans 1,2-diol. Notice the stereochemistry. Trans. It can be written differently, applying some of the chemistry we learned from earlier chapters. The chair conformation of cyclohexane is a very stable conformation. If you draw the chair conformation, this is the trans arrangement where the groups are in the equatorial position. So either one will be acceptable answers. As you can see in organic chemistry, your answers are getting in the range that you can use represented different ways. You have a choice in terms of the answers that you can present, and it's not just one specific answer. Here's another example. Here's your alkene. First reactant is MCPBA, metachloroperoxybenzoic acid, an oxidizing agent which will oxidize your alkene to get the epoxide. In a second step, this time it's water in the presence of a base. So it's a basic oxidation. Here we have our trans alcohol. Notice here we're using dash and wedge to indicate the stereochemistry. So if you're asked to write the product of a reaction and indicate stereochemistry where appropriate, you would have to utilize the dash and the wedges to indicate stereochemistry. Okay. Let us look at another reaction in terms of the epoxide or the oxirane. This time it's a nucleophile that is not water. So let us look at the general reaction here, Nu negative. If it's Nu negative, as you can imagine, it's in a basic medium because you cannot have Nu negative in the presence of H+. So it's Nu negative. This Nu negative will attack the carbon that's less crowded. So notice this carbon here has two alkyl groups. This carbon has two hydrogens. So this carbon here is less crowded compared to this carbon. So a nucleophile will attack this carbon in a basic medium to produce this. As you can imagine, using the arrows to indicate electron movement. And in a second step, you can have here your water. So this is step 1. In a second step, your water will protonate this O negative to produce here again your trans product. Trans product. Here's a practical example. Here's your alkene. First reaction is with MCPBA to form the epoxide. This time we're using a methyl grignard. Notice a methyl grignard. A methyl grignard is a highly basic nucleophile. It's a reducing agent, but a highly basic. So in a second step, it would attack this carbon since it is less crowded, because there's one hydrogen here and there is no hydrogen here but alkyl groups. And in a third step, we can add proton to put on the OH, the H. So here is the trans arrangement here for the methyl group and the OH group. In the presence of an acid, so in an acidic medium, this reaction will still occur. As you can see here, if there's an acid present, it will protonate to form this protonated oxygen. These carbons here are still positive, but the nucleophile in an acidic medium will attack the more crowded carbon. You can imagine this more crowded carbon is more stable because it's carbocation-like, and we have alkyl groups to stabilize that. So this nucleophile, which is now neutral in an acidic medium, will attack the more crowded carbon to produce here the trans product. As an example, here is an epoxide, which you can make, of course, from MCPBA, but in the presence of HCl, which is really H plus and Cl minus. So here's your nucleophile, here's your acid. You will get here the trans product. This is the minor product, but this is the major product where the Cl will attack the carbon, which has the more groups bonded to it, or the more crowded carbon. Okay, let us look here at another type oxidation, and this one is using KMNO4 in water. So here we have an alkene in potassium permanganate. By the way, this should be a small n. Using potassium permanganate, what you'll get here is a cis-diol. Notice this is a cis-diol, not a trans. A cis-1,2 diol. Same reaction here, but instead of using potassium permanganate, we use osmium tetroxide in the presence of hydrogen peroxide to give the cis-diol. Based on my philosophy and teaching, you can memorize this if you want, but I prefer you not to just memorize it, but to know exactly why these reagents here, they give cis-diol and not trans-diol. So we'll have to look at the mechanism. So let's briefly look at the mechanism. Here's the permanganate, the anion, potassium permanganate. You will notice here that the reaction involves these two oxygens from the permanganate attacking the carbons of the alkene, and they are now situated on the same side of the carbon-carbon bond. Hydrolysis will break, of course, these bonds right here to give the syn or the cis-diol, the OHs on the same side. Same aspect here. This is the osmium tetroxide. Put the OHs on the same side because they're coming from the same molecule. The reaction with hydrogen peroxide will break this bond, and you will have here the OHs on the same side, or a syn addition, or a cis-1,2 diol. So once again, you can get a trans-diol or a syn-diol depending on the reagents of choice. So let us see if we can apply what we have just learned here to the synthesis of this molecule. So here's your starting material. Here's the target molecule. Notice the stereochemistry. Dash and wedges. As you can imagine, or as you guys know, that in natural products, especially in the pharmaceutical industry, most of these compounds have specific stereochemistry because the body is specific for molecules with have specific stereochemistry. So here is a molecule that has specific stereochemistry. So the question is, how do we make this molecule, or how do we synthesize this molecule? If your job was, this is your starting material, pretty cheap, but this is what you need as your target molecule. Based on my approach in teaching, make your observation and come up with a strategy how to synthesize that. Remember, chemistry and science is based on observations and a conclusion based on your observation, or carrying out an application of these observations and strategy. So let's start by analyzing our target molecule here. The first thing that we will observe is the stereochemistry. The OH and this alkyl group, ethyl group, are trans to each other. So that should ring a bell, saying we can get a trans OH from an alkyl group by doing a Grignard reaction with an epoxide. Okay. Next we look at, how do we make an epoxide? We make an epoxide from an alkene. Here we have bromine in the reactant, and we know if we had an elimination reaction where bromine and one of these hydrogens are eliminated, we have an alkene. So that's our observation, our observations. And we now have a strategy. We need to put this information or these observations together to come up with a strategy to communicate the synthesis of this target molecule here from this reactant. So, putting that together, starting of course from our reactant, if we had this epoxide here, we could react it with ethyl Grignard. Here's the ethyl group with the epoxide, and it's going to attack at the least hindered carbon, and the OH would be here. How do we make an epoxide? We make an epoxide from MCPBA with an alkene. So once you have this alkene, you can carry out this reaction here using an oxidation reaction. A reaction that we'll have to remember from earlier chapters is the elimination. So in the presence of a strong base such as potassium hydroxide, alcohol as a solvent, and heat, we have elimination reaction where the Br and one of these H's will come off to form here the alkene. So that's how we communicate the strategy of transforming a reactant molecule, starting material, into a target molecule here as our product. Let us look at another oxidizing agent. Really, it's the same oxidizing agent, potassium permanganate, but the difference here is we are applying heat. So it's carried out at elevated temperature. So as you would expect, the first reaction is to produce the 1,2-diol. But because the reaction conditions are at elevated temperature, it will proceed to break this bond here to produce a ketone or an R ketone, and of course the oxygen, and it will produce an carboxylic acid, where this R is a R from the alkene, but notice this H here is gone, or that H has been abstracted, and now we have an oxygen. This H is lost. Now we have an oxygen. Why do we have an oxygen? Because we have a strong oxidizing reagent as our reactant. So the aldehyde will form, but readily, as we have seen earlier, transform into the carboxylic acid. So you will not isolate the aldehyde, but in this case you will isolate the ketone and the carboxylic acid from an alkene of this type. Another reagent is ozone. It's an oxidizing agent, as you can imagine, O3. If you react that with an alkene, the initial reactant product is an ozonoid, not isolated. React this with dimethyl sulfide, it breaks the bond to get a ketone, and in this case, notice the difference, we have the aldehyde which maintains that H. So two different oxidizing agents breaking the carbon-carbon double bonds, but producing different products based on what's bonded to the carbon of these bonds. Let us apply that information. This time the application is a little different. We're not using it to synthesize a target molecule, but in this case we're using it to determine an unknown compound. So if we have an unknown compound, so let's say your first day on the job as a chemist is to determine the structure of an unknown compound. You could subject it to KMNO4, there should be a small n, which I'll correct, and heat. It will break the double bond if there is a double bond there. So if there is a double bond and you use your spectroscopy techniques to determine the structure of the products, and you determine one is 2-propanone and the other one is ethanoic acid, in reverse thinking you can apply that knowledge to determine what is the structure of this unknown compound. Okay, here's another example. If you had an unknown compound and you subject it to KMNO4 and heat, if there is a double bond, carbon-carbon double bond present, it's going to break it. This time, however, you do not get two molecules, but you get one molecule, which is a dicarboxylic acid. Two carboxylic acids that are present. What is the structure of that unknown compound? As you can imagine, this requires a lot of thinking, a lot of analytical thinking to put the pieces together. And as I keep pointing out in lectures, this is another reason of the importance of organic chemistry, because it assists in developing your critical and analytical thinking skills. So the question now is, what are the structures of these starting materials given these products upon oxidation with potassium permanganate in the presence of heat? Let's see. So if we had propanone, we know that this carbon here was bonded to this carbon here in a double bond. So we simply make a carbon and they're bonded together. We put the groups on. Here are the methyl groups on that carbon. This carbon here has a methyl group. Here's a methyl group, but it has here an OH, a carboxylic acid, which means that it had a hydrogen right here. So this would be the starting material, or 2-methyl-2-butene as the starting material. Here's the other one. we know that in the reactant, this carbon is bonded to this carbon. So one way of thinking about that, it's a ring. So here are these carbons of the double bond. Now we're breaking that, but notice carboxylic acid, which means that we have a hydrogen here and a hydrogen here. So this would be here the unknown reactant. Let's see how that would differ if we use a different oxidizing agent. In this case we use ozone, so this type of reaction is called ozonolysis because we use ozone to break the carbon-carbon bond. We know that ozone followed by dimethyl sulfide breaks the carbon-carbon double bond, and here are the products. So we know that this carbon was bonded to this carbon. And notice the H. H remains because it's not as strong an oxidizing agent as your potassium permanganate. Look at this one, H and H. Not the carboxylic acid because the ozone in dimethyl sulfide is not as strong an oxidizing agent as our potassium permanganate. So, as you can imagine, here are the unknown starting materials. Same here, but in this case, the aldehyde maintains and is not oxidized further to the carboxylic acid. Here the aldehyde maintains and is not oxidized to the carboxylic acid. So here are the starting material for these reactions using ozonolysis. So ozonolysis is used quite a bit to determine the structure of an unknown compound based on the functional groups of the products that are produced after oxidation. Let us turn our attention briefly to the oxidation of carbon-carbon triple bonds or alkynes. As you can imagine, KMnO4 will add your OHs onto the pi bonds. It'll react right here. And in the presence of an acid in the second step, you can imagine now this is not stable, as you can imagine. Lots of groups that have the potential of leaving in the presence of an acid. So if you protonate one of these OHs here, it can leave as water, and you can lose another molecule of water until we get down here into the final product, which is a diketone. Notice this is an internal alkyne where we have two R groups on either side of the triple bond. So we have a diketone as the final product. So if you have an alkyne and you react it with potassium permanganate as an oxidizing agent, you end up with your diketone. Notice it's a 1,2 diketone or an alpha ketone. In the presence of a terminal ketone, notice terminal because it's at the end, because this is a hydrogen. So this is an R group back here, and the alkyne is now at the end, so we describe that as a terminal ketone. In the presence of KMnO4, an oxidizing agent, we have the same type addition here. In the presence of an acid, water will leave and water will leave here, and we end up with an aldehyde. But as you can imagine, in the presence of a oxidizing agent such as KMnO4, it will oxidize to the carboxylic acid, and now we have an alpha keto acid. As you know, this is a very important tight molecule in biology, the alpha keto acids. So this is how you can make an alpha keto acid from a terminal alkyne. Lastly, we look at the oxidation of aromatic compounds. We just briefly introduced aromatic compounds when we looked at functional groups, but next semester we'll have a couple of chapters just based on the reactions of aromatic compounds. Benzene, this is the benzene ring system here. If there are two OHs bonded to it, it's easily oxidized using silver ions to get the quinone. So here's the quinone oxidized product. Here's another example. Here's another example of an aromatic system here. This is two benzene rings that are fused called naphthalene. So if that's oxidized, here's a strong oxidizing agent. We have this as a product as a metadione, and of course, as you can see here, especially in biology, it's very similar to vitamin K and used in the biological systems. Another and last example we have here is coenzyme Q, ubiquinol. You can see here is the aromatic system, and if it's oxidized, it goes to the coenzyme Q, the oxidized form, ubiquinone. And of course, if it's reduced, and of course we know how to do that reduction with lots of reducing agents that we studied from last chapter, we can go back to the coenzyme Q or the ubiquinol, the reduced form. So this is a practical example of oxidation reduction as it relates to biology. This is the last slide of this chapter. So go ahead and continue to read your text and go over these slides. And as I mentioned earlier, you may want to pause these slides at different points, get to your notebook and write these reactions out. Make sure you understand the concept of each reaction, because I'll be emphasizing the application of these reactions to solve different problems. And of course, you'll have to communicate on paper how you have utilized these concepts to solving problems. So continue to study hard. This is the last chapter for this semester. So we have made it through the fall semester. Looking forward to working with you next semester. And we'll start chapter 12. So continue studying. This material will be on the final exam, which is an ACS standardized exam. I'll say more in a communication. So once again, keep up the hard work. We're almost there. Okay? Bye.